turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. Coming up is elite-level sport linked with motor neurone disease. We examine the evidence as another top-level player announces his diagnosis. Also, cages that can sieve out molecules, the immune system peacekeepers and the quantum realm. We delve into this year's Nobel Prizes for science. And how did birds react to the Great American Eclipse last year? First this week, motor neurone disease, or MND, is a devastating condition that affects the motor nerves that convey movement instructions to our muscles. It normally affects people over the age of 60, but recently there's been discussion about whether professional contact sports, like rugby, might increase the risk of developing MND. One high-profile case is former England captain Lewis Moody, who told the BBC about his diagnosis just recently, aged 47.
A couple of months ago, noticed that I was getting shoulder weakness and went and saw our physio. Kerry did a fantastic job, gave me some rehab stuff to crack on with, and nothing really changed over the course of sort of 6 to 8 weeks, at which point he referred me to a brilliant shoulder specialist. I had an MRI, neck scan, all that type of stuff. And very quickly when the scans came back, it became clear that it wasn't anything to do with the neck, despite all the years of sort of throwing myself into contact on the rugby pitch. And he then sent me straight to the neurologist, and off the back of the MRI, he actually had a phone call with me where I sensed he was preparing me for the worst, which was fairly difficult information at the time to receive, I suppose. But we processed lots of emotions over the last couple of weeks, and I suppose when you talk about it, and I generally feel fine when you talk about it, it's never me that I feel sad for. It's the sort of sadness around having to tell my mum, as an only child, and the implications that has for her. Having to tell the boys, two brilliant boys, and that was pretty heartbreaking, wasn't it? But
Lewis Moody isn't the only professional athlete to be diagnosed with the condition. Former rugby players Rob Burrow and Doddy Weir both died of the disease, and Gloucester's Ed Slater was forced to retire early from rugby in 2022 following his diagnosis. I've been speaking with Mike Rogers, who's Director of Research and Innovation at the MND Association.
motor neuron disease affects motor neurons. These are nerve cells that are found in the brain and in the spinal cord, and they tell our muscles what to do by relaying electrical signals to them from our brain. In MND, messages from the motor neurons stop reaching the muscles. The motor neurons die, and those messages don't get through from the brain. This affects movement, it affects speech, swallowing, and breathing.
Who tends to get this? Who does it most often affect?
That's a really good question. It tends to affect older people more. That's a risk factor. But other risk factors aren't really as well known. It tends to affect more men than women. But beyond that, it's quite difficult to tell who might get MND.
And how will a person who's getting it know that something's up? What do they notice?
So this can vary. So onset and symptoms and the progression of the disease can be quite variable in people. Generally speaking, you'll notice things like muscle wastage. You might have a few falls. You might notice some differences in your swallowing. And this will be different for different people. But it's those sorts of things that people tend to notice and go to their doctor about.
And then the natural history, what tends to happen once a person's got symptoms they're noticing? How does it progress?
MND is a progressive disease. It's always fatal. The symptoms and the progression can be very, very variable in people and how they experience them. Some people have their movement affected very quickly. Some people might be able to move for longer, but might have their speech affected. So those symptoms and the progression of those symptoms can be very variable in different people. About half of people die within 2 years of a diagnosis, but then there's a number of people who live quite a lot longer than that afterwards. So it is a very, very variable disease in the way that patients experience it.
If we put sportsmen and women to one side for a moment, what do we think is the main reason people get this? What underlies the disease process?
In 85% of cases, we just don't know. This is what scientists are trying to unpick. We know a lot more about the biology of the disease than we did 10 or 15 years ago, and we've seen a huge upsurge in its research, but we still haven't pinpointed that cause in the majority of cases. In about 15% of cases, there is a well-defined genetic cause, and we're starting to develop treatments for those now.
And in relation to sportsmen, women, rugby players, and so on, what's the evidence that there is an association between people who are doing high-performance sports and are developing motor neuron type problems?
So this is still quite uncertain. We don't really know. There's not enough evidence at the moment to really show a firm link. Previous studies have looked into things like, does exercise or head impact during contact sport increase your risk of getting MND? And some of these studies have suggested that being an NFL player or being a footballer or being a professional rugby player may increase your risk of having MND. These studies are of interest, but they don't demonstrate a cause or that it's the sport itself that's causing this. Also, MND is rare, relatively rare disease, so numbers in these studies are quite low. So quite a lot of care is needed in drawing conclusions.
Are there any mechanisms that we can invoke to say why individuals who are extremely sporty might be at higher risk of this happening to them?
There's been a very recent study, which has been led by a group in Sheffield, which has looked at the link between exercise and risk. And this has been a really interesting study. The data suggests that for a very small proportion of men who undertake what they describe as extreme exercise, this extremely high intensity exercise, there's some sort of association with a loss of function in key genes. And what may be going on here is the protective mechanisms are being switched off, causing this very small subgroup to be more likely to develop MND.
What do you think we can do about it? Given that we don't know the cause at the moment, and we just know that there are these possible associations, how should we and how are you pursuing this? And what should be the next steps?
We've recently funded a couple of studies. One is a study looking at much larger numbers of footballers. A problem with a number of the studies that have been done so far is that they're relatively small. Can you look at bigger groups? And looking at those bigger groups will give us more resolution effectively in some of these findings. So there's a study going on looking at footballers and their death certificates. That's in England and in Italy. Hundreds, thousands of footballers try and unpick this a little bit. There's also another really interesting study that we funded with a couple of other charities. And that is looking at rugby players and looking at repeat physical trauma and whether or not something that happens in the cells can actually be measured, taking blood samples from professional and academy rugby players to investigate this and to see if they're different compared with blood samples from non-contact athletes. And what they're trying to do here is identify the pathways that may be contributing to the development of MND. There's also a study that was published last week into traumatic brain injury. Previous studies have been done on this, but again, they've been relatively small and confined to specific groups. This was done by Willie Stewart. It was funded by us and a couple of other charities. And he was looking at healthcare records of 340,000 people. And what he found was those people with a history of traumatic brain injury, and that can range from anything from concussion, a mild type, to more serious types of traumatic brain injury, are more than twice as likely to receive an MND diagnosis than those who haven't had a traumatic brain injury. However, what that team also found is that the increased risk was also only confined to the first 2 years after the injury. And what this suggests is that in some cases, the brain injury might actually be an early sign of MND rather than its cause. So, for example, you've got early MND, you might not know, and you would have a fall that causes that injury. So again, more research is needed there, but that's a really, really interesting piece of work into the connection between brain injury and MND.
It's an interesting conundrum, isn't it? But as Mike Rogers at the MND Association we were listening to there said, we do know a lot more about the disease now than we did just a decade ago. So let's hope that rapid rate of progress soon bears fruit. Every October, the world's spotlight turns to Stockholm as the Nobel Prizes celebrate discoveries that reshape our understanding of life and the universe. Later on, we will unpack the prizes in physics and in medicine. But first, we're turning to chemistry. With a rundown on who's won what and what for, here's Alice Archer.
The 2025 Nobel Prize in Chemistry has been won for the development of metal organic frameworks by the University of Melbourne's Richard Robson, Kyoto University's Susumu Kitagawa, and University of California, Berkeley's Omar Yagi. Metal organic frameworks, or MOFs, are three-dimensional molecular cages composed of metal atoms joined by organic linkers. They enclose cavities which can be used to capture and store other molecules. They can hold large amounts of hydrogen gas, for instance, and also filter out greenhouse gases like CO2 or methane from flue streams. They might also be able to work as magic bullets in the body, discreetly dispensing sequestered drug molecules into just those disease tissues that need them. MOFs owe their existence to the vision of Robson, who in the 1980s envisioned using metal atoms as nodes and carbon-based organic molecules as struts to link the nodes together. In a proof of concept, an MOF comprising copper atoms joined by a four-armed organic molecule assembled itself into a repeating diamond-like configuration, with a generous cavity at the center of each repeating unit. It was a brilliantly simple yet powerful idea that provided the framework upon which the field would subsequently be built. Robson showed chemists how to think like architects on a molecular scale. Inspired by the concept, Kyoto-based Kitagawa went a step further. He created flexible frameworks whose pores could open and close as guest molecules were admitted, demonstrating that MOFs could also be smart, responsive materials, and opening the door to the creation of sophisticated molecular machines capable of sensing and sieving substances. Yagi, meanwhile, had perfected the art of reticular chemistry, stitching molecular building blocks into strong, predetermined structures. Applying this to metal organic frameworks, he created MOF5, a crystal that is incredibly light, yet has an enormous internal surface area. A single gram has the same surface area as a football pitch. This was the opportunity the field had been waiting for. With this technology, MOFs could operate at scale and potentially solve real-world problems. In the years since, chemists have built tens of thousands of different MOF molecules, combining different metals and organic linkers to produce materials with different architectures and capable of grappling with some of humankind's greatest challenges. Applications include separating PFAS, forever chemicals, from water, breaking down trace pharmaceuticals in sewage, capturing carbon dioxide, and even harvesting water from desert air. For decades, scientists have dreamed of engineering atoms to produce molecular machines with defined functions. Now, thanks to these three chemists, it's really happened.
Alice Archer. Stay tuned for physics and medicine Nobels coming up later on. But first, scientists are using the James Webb Space Telescope to gain fresh insights into the atmospheres of distant exoplanets. The research, which has been published in the journal Science, aims not just to learn about that atmosphere though, but to use the information to reveal what these distant worlds are made of too. Oliver Shortall is from the Institute of Astronomy at the University of Cambridge.
We've been presented with this fantastic diversity of worlds beyond our solar system, from Jupiter-sized planets pretty much kissing the face of their star, they're so close to it, all the way out to Earth-sized rocky planets. And in between that lies a sort of zone of mystery, which are these planets that are a bit bigger than Earth, a bit smaller than Neptune, that we have no example of in the solar system. And they've been discovered in most cases by them passing between our line of sight and this distant star and causing a brief dimming of the light from the star as they pass in front of it. So that tells us they're there, and it tells us something about their size. But to then build a more detailed picture, we need to start understanding their composition. And we can get an idea about their composition if we weigh the planet, if we find out how massive it is. And we can do that by looking at the effect the planet has on the star. The planet tugs on the star with its gravity, and that causes a wobble in the starlight that gives us a hint about how massive the planet is. And with those two pieces of information, we have the first step towards building a more detailed picture of the planet, and that gives us its density, which critically tells us how much rock there is and how much gas. And the more rock, the denser.
But what's the next step? Because we've been doing that, as you say, for a while now. We've begun to get some insights into where these things are, how many of them there are, what they might be made of. But how can we go a step further now?
Yeah, so to go further than that is really an area that's been opened up with first Hubble, but now the James Webb Space Telescope. And what those observatories allow us to do is start looking at that tiny fraction of starlight that passes between the star and our eyes, but through the atmosphere of this distant planet, which allows us to compare the density that we've estimated now with an insight into the gases that are making up the atmosphere. And that begins now to connect to the interior of the planet.
So there is a relationship between what is in the atmosphere and what the planet's made of.
Yeah, exactly. And not only what it's made of, but also the climate of the planet. So on Earth, for example, the composition, the chemistry of Earth's atmosphere both decides the climate, as we're well aware of, with the amount of carbon dioxide in Earth's atmosphere changing how hot the planet is. And when the climate gets changed, it changes how the atmosphere interacts with the interior of the planet. So on Earth, a lot of that interaction is happening through liquid water, dissolving rocks, drawing carbon dioxide out of the air. On a much hotter planet, if you go to the extreme and get really hot, the planet will melt. And now you've got an ocean of magma at the surface of the planet that's rapidly exchanging gas with the atmosphere. And now the atmosphere is sort of directly seeing into the interior of the planet across this atmosphere magma interface. What we're announcing is a framework now for thinking about this diversity of planets that we've discovered, all the way from bare rocks that are so brightly illuminated by their host star that all the atmosphere has been blown away, out to this other extreme, and this is the sort of frontier now, these planets that are intermediate in size between Earth and Neptune, where we've got no example in the solar system, and we have to work everything out through the light that we can get from these distant stars that's passed through their atmosphere. And these are worlds which potentially have vast, thick layers of gas and possibly water at their surfaces, asking questions about climates and interiors, and possibly also habitability and the ability to host life.
Given we can't go there to actually say, well, has Oliver got it right? How do you know that the inferences you're drawing are the right ones?
And that's the really key challenge that we now face. This field is enormously rich because it can't advance just with the astronomical observations alone. That needs to be coupled now with experiments back on Earth in laboratories, subjecting materials, water, rock, to the extreme pressures and temperatures that are found in these exotic exoplanets. We can bring all of these disciplines together and ask the question, is the atmosphere we're seeing consistent with these different types of interiors that might be there?
Have you therefore got a kind of a prediction for what a certain body with a certain atmosphere and a certain surface profile would look like, so you can then kind of compare what you see with what you think you should see if it fits that model? Or are you observing things and then going, that's interesting, how do I explain that? Or is it a bit of both?
Yeah, exactly. So we're both working on fingerprinting from doing the calculations, the models, what these atmospheres should look like for certain interiors, certain climates, certain compositions, and at the same time being challenged by the new data that comes in, that in some cases doesn't see an atmosphere at all, and we have to understand that, and in other cases sees an atmosphere, but we're not quite seeing the gases we expect. So we've got to ask ourselves, well, this gas is missing. Is it because it's hidden in the inside of the planet? It dissolves really easily into a liquid water ocean or a magma ocean? Or is it some other aspect of our model is wrong?
What sets this apart from just stamp collecting, though, Oliver, going around, roving around the galaxy now, looking at interesting stars that have interesting planets around them and asking this sort of question and then sticking another stamp in your sticker book saying, well, we know what that one's made of? How does this actually move us forward?
What we're doing is we've got this now range of natural laboratories to investigate the fundamental processes that shape planets from their formation through then their teenage years into their middle ages, and asking now what needs to happen to leave a planet habitable and inhabited. The key question here is, are these planets a bit bigger than Earth, or are they something completely different? We don't know how big a planet can be before it stops being sort of just an inflated Earth and starts being something completely different, like Uranus or Neptune.
Exciting and intriguing. Oliver Shortall looking at planets light years away and working out what conditions there might be like.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is The Naked Scientists with me, Chris Smith, and still to come, we'll hear how birds reacted to the Great American Eclipse of 2024. Before that, though, time for the second of our Nobel Prize updates, and this time, the award for medicine. Alice Archer again.
The 2025 Nobel Prize in Physiology or Medicine has been awarded to Mary Brunko of the Seattle Institute for Systems Biology, Fred Ramsdell of Sonoma Biotherapeutics, and Shimon Sakaguchi from Osaka University. Their discoveries have solved a crucial question in immunology. Why does the immune system usually not attack our own tissues? It's down to, they found, a specialised cell type that acts as the immune system's dedicated peacekeeping force. These cells, known as regulatory T cells, prowl around the body, damping down immune responses to targets that the immune system should ignore. A good example is the developing baby inside a pregnant woman. It's 50% genetically unrelated to her. If it were a donated kidney, it would be wiped out in hours, but thanks to regulatory T cells in the placenta, the immune response is persuaded to look the other way and adopt a state of tolerance. Previously, immunologists thought that immune tolerance of this type could only be achieved by any self-reactive immune cells being eliminated in the thymus, an immune organ active mainly early in life. Now, thanks to these Nobel laureates, we know better, and our understanding of processes like autoimmune disease, allergy, cancer, and organ transplantation has been revolutionized. The story begins with experiments carried out by Sakaguchi in the 1980s. He had identified immune T cells carrying a specific marker known as CD25. These cells, he found, had a remarkable function. They actively suppressed other immune cells and prevented them from launching self-destructive autoimmune attacks. He named them regulatory T cells, or Tregs. The work showed that immune tolerance is an active, ongoing mission carried out by these elite cellular guardians. Subsequently, across the Pacific in 2001, Brunko and Ramsdell provided the critical genetic key to understanding these peacekeeper cells in humans. Working together, they linked an autoimmune disease in mice with mutations in a gene called FOXP3. Mutations in the human equivalent of this gene, they also found, caused a serious autoimmune disorder. 2 years later, Sakaguchi linked these discoveries. He proved that the FOXP3 gene encodes a master switch that instructs T cells to become the Treg cells he discovered years before and take on their protective role, monitoring other immune cells to ensure that our immune system tolerates our own tissues. The discoveries of these three laureates have unlocked an entirely new branch of immunology called peripheral tolerance. By learning how to manipulate Tregs, scientists are now developing therapies to boost their activity to treat autoimmune diseases like rheumatoid arthritis and multiple sclerosis, or to suppress their activity in tumours, allowing the immune system to attack cancer cells more effectively. Congratulations to all three on this incredible and richly deserved prize.
Alice Archer, and Alice will be back a bit later on to unpack why the quantum world has now been recognised in the prize for physics this year. During the Great American Eclipse in April 2024, daytime turned to near night for a few minutes, and birds, as it turns out, went haywire. Some fell silent, others sang as if dawn had come again, and many launched a false dawn chorus once the sun returned. Scientists decided to plug into this rare natural experiment and also tapped up citizen observations and used machine learning to see how sudden changes in light can upend a bird's daily rhythms. I've been speaking with Dustin Reichard at Ohio Wesleyan University.
We're really interested in how birds would respond to the solar eclipse. And the eclipse was very strange for birds. Humans had the benefit of knowing when it was going to happen, how long it was going to last, and what was going to happen afterwards. Birds had no idea. They had not experienced anything like this at all in their lives. And so it was a normal April afternoon. They were setting up territories, singing for mates, getting ready to breed, and the sun disappears for 4 minutes. And we wanted to know if they would respond, and if so, how they responded.
Did you set up the study in advance because you knew this was going to happen? So you thought this is a wonderful natural experiment to do to see how nighttime coming for a short while when birds are not expecting it is going to affect their behaviour?
Yes, so we wanted to collect as much data as possible. The eclipse began in Mexico and traveled across the central and eastern United States and just in the far eastern tip of Canada. So there was a broad range where we could have collected data, but we couldn't be everywhere at once. And so Liz's idea was to develop a phone app. Anyone with a smartphone, regardless of whether they had watched a bird before, would be able to download this app, open it, and report to us what they observed birds doing during the eclipse. And they could do this multiple times. And this allowed us to gather tens of thousands of data points, right, from all over North America, which was an extraordinarily large data set. We also wanted to go in and collect some localized data too. So we set up these passive recording units, which are basically just microphones with batteries attached to them. And we put them all around Bloomington, Indiana, a Midwestern city, where the eclipse was going to last for about 4 minutes. And so in addition to the data collected by the public, we had these recordings of the days leading up to the eclipse, what happened during, and then the days after the eclipse. So we could see how the birds' vocal behavior, their songs and the calls, changed, if at all, during the eclipse relative to a normal April afternoon.
And did it?
It did for most, but not all birds, which was really interesting. So if we look continent-wide across all the data collected by the public, we saw that after the eclipse, they started to move around more and they vocalized more, almost like this new dawn chorus, right? So if the eclipse was kind of a mini night, when the sun came back, they started to move around and vocalize more. And when we looked at the data from the recordings in Bloomington, we saw very similar things. We had 52 species that we were able to identify on those recordings. 29 of them had a substantial change either before, during, or after the eclipse compared to a normal day. So the days before and the day immediately thereafter. The majority of those increased how much they were singing and calling. So they got more vocal.
What about nocturnal birds, owls and so on? Did you see any behaviour change from them?
We did. So the most notable one were the barred owls, which typically they're crepuscular, which means they're active most right around dawn and dusk. So they're kind of particularly sensitive to that transition period in light. And we saw that they vocalized about 4 times more during the eclipse than they did on a normal April afternoon. As it got darker, they became more vocal and presumably more active. This is a period when they're hunting and capturing food, and so it matched the predictions really nicely.
And was there any hangover effect? So once the eclipse resolved and then the birds demonstrated the post-eclipse behavioural changes you've just documented, did they then go back to normal and then have a normal rest of the day? Or was it almost like Groundhog Day and the time had started again and they ended up staying up later that day?
We don't actually know whether they stayed up later. I'd suspect not, because they are sensitive to when the light shuts off. That's a big signal for them. And so I would have expected them to finish their day as expected. There was this big burst right after the eclipse, kind of in the 12 minutes after, and some species were affected there. And then they seemed to calm back down. And there was a different set of species that were also affected a little bit later, kind of 30 minutes after the eclipse ended and the light intensity increased. Then they had a burst of vocal behavior, songs and calls, as things were kind of getting back to normal.
What do you take away from this then? It's sort of, in some respects, predictable that the birds, they're very visually guided, visually driven creatures, and therefore it's not surprising that they would think, oh, it's nighttime, and go to sleep, or make preparations to go to sleep and then wake up when the sun comes back, and albeit a short night for them. But are there any broader implications and applications of this amazing natural experiment with this huge amount of data that you've now managed to accrue?
Definitely. So we had a majority of species where we saw substantial effects, but there was also this decent chunk that didn't really respond at all, at least based on their vocal behavior. It was the same as they were the day before and the day after. And so, what causes that? What makes some species more sensitive to light to where they respond to this disruption? And then there's this subset that just don't. And so, we've been doing a lot of experiments that are the opposite, where we're adding light at night, right? When it shouldn't be dark, we're adding light and we're seeing these tremendous effects on species, how they behave. It's affecting the timing of their breeding, when they sing. And this can be costly for these birds. And as human population growth continues, the world gets lighter and lighter at night. There's going to be species that are more sensitive that are going to be more affected, potentially in negative ways. So being able to go in and say, yes, these species were really affected by this change during the eclipse. Perhaps they're going to be more affected at night too, as we continue to increase our light pollution. But there's this subset that aren't. And so maybe the fact that they're less sensitive to these changes in light, they're more protected.
What a great piece of work. Dustin Reichard at Ohio Wesleyan University there, and he reported those findings just this week in the journal Science. Well, now it's time to make a genuine quantum leap into the Nobel Prize for Physics. Alice Archer again.
The 2025 Nobel Prize in Physics has been won for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit by the University of California, Berkeley's John Clark, the University of California, Santa Barbara's Michelle H. Devereux, and John M. Martinez. Their work brings the quantum computer a step closer to everyday reality. Unlike conventional processors, which work in binary bits, zeros and ones, or black and white, quantum computers work with quantum bits, called qubits. And rather than just a black or white state, these can encode the entire grayscale in between, potentially unleashing computing power capable of achieving in a fraction of a second what the best supercomputers currently take years to calculate. Clark developed a device that could read this qubit information. The SQUID, or Superconducting Quantum Interference Device, is the ultimate magnetic field detector. It's so sensitive it can measure the faintest magnetic whispers, even those produced by a single quantum bit flipping from a 0 to a 1. Without the development of these ultra-precise measurement tools, the dream of building a quantum computer would not be possible. Clark's work provided the essential lens through which we could finally see and interpret the quantum world. Meanwhile, at Yale University, Devereux was tackling the problem from a different angle. A pioneer in the field of circuit quantum electrodynamics, he built some of the first superconducting qubits. He figured out how to design electrical circuits capable of behaving like artificial atoms. In these circuits, electrical currents can exist in a quantum superposition, being both on and off simultaneously. This is a grayscale that makes quantum computing so powerful. The crucial breakthrough, though, came from Devereux's designs, which meant qubits could be protected from environmental noise, a critical step in making them useful for computation. But building a few good qubits is one thing, building an army of them that can perform a task beyond the reach of any classical supercomputer is another. After a distinguished career at the University of California, Santa Barbara, Martinez took his expertise to Google. There he led the team that designed and built the Sycamore processor. In 2019, he and his team announced a milestone that shook the world. They had achieved quantum supremacy. Their 53-qubit processor performed a specific calculation in 200 seconds that would take the world's most powerful classical supercomputer an estimated 10,000 years to complete. Martinez demonstrated that quantum computers weren't just a theoretical possibility, but a practical reality with world-changing potential. Scientific advancements are led by technology. The incredible work of many academics would not be possible without the high-speed computers we have today, but the capabilities of classical technology are plateauing. The next quantum leap in computing will genuinely come from this realm. The amazing work of these three scientists has led us to the cusp of a breakthrough. And in closing, I'd also like to say three of last year's winners, Demis Hassabis, Geoff Hinton and David Baker, have been on our show previously. So, John, Michelle and John, if you're listening to this, we'd love to have you join us too. Congratulations to all three on a prize so thoroughly deserved.
Thanks, Alice. Alice Archer, our intern this year from Queen's College. Now, from the quantum realm to question of the week, and James Titko is under the pump thanks to this inquiry.
Ian Madley from Stockport here. Urban heat domes caused by density of heat sources are well known. Almost all of this heat is generated from fossil fuels. As we move to heat pumps, particularly air source units, which draw heat from the ambient air, my question is, will this impact the heat dome effect?
Thanks, Ian. Urban heat domes, or heat islands, are ways of describing the relatively higher temperatures in cities compared to surrounding rural areas. But the main reason for urban heat islands is in fact the difference in topographies between city and countryside. Dark surfaces like concrete and tarmac absorb much more solar energy, while a lack of vegetation reduces the amount of cooling by evapotranspiration. So what effect might heat pumps have on all this? Well, first, we should explain how these devices work to move existing heat from a cooler place to a warmer place. Here to help is Professor Bob Kreitov from the University of Warwick's School of Engineering.
The principle is just the same as what goes on in everyone's refrigerator, except in the refrigerator you're interested in the cold end. In the heat pump you're interested in the hot end. At the simplest level, what the refrigerator is doing is using a bit of electricity to suck heat out of the food inside your fridge. And then it has to put that heat somewhere out of the back of the refrigerator where the condenser is. And just conservation of energy, the heat that comes out the back is going to be the sum of the heat you've extracted from the food inside plus the electricity you used. So more heat comes out the back than electricity used. And with an air source heat pump, it's exactly the same. You're cooling a load of outside air using electricity and dumping that heat plus the amount of electricity that you've used inside the house. So typically with an air source heat pump, if you use 1 kilowatt of electricity, you'll suck 2 kilowatts out of the outside air, 3 kilowatts go inside your house. And that's what's called a coefficient of performance of 3.
Transferring thermal energy from outside to inside will indeed reduce the temperature outside, as you suggest, Ian. If you take these rough numbers of for every kilowatt of electricity you use, you've got 3 kilowatts of heat inside your house, compare that with burning 3 kilowatts of gas to do the same thing. You've reduced the heat island effect from heating your home by 2/3. As we mentioned though, combustion for human activities isn't the main driver of the heat dome effect. But the even bigger caveat is, we're not so worried about the heat island effect in the winter, when heat pumps are likely to get the most use. We're worried about it during the summer, when we're in fact likely to be using air conditioners operating on the same pump and refrigeration cycle, but which transport heat outside.
Yes, sadly that's true. So as the climate changes and more people want air conditioning in the cities, it feeds on itself and everything gets worse. All that electricity used ends up heating the environment, so you need a bit more electricity to cool you down in your building. It's a bit of a vicious circle. The only way to get around that would be if actually within the city you had lots of PV panels making electricity which was sufficient to power the air conditioners. So it would be solar powered air conditioning.
Thanks so much for such an interesting question, Ian. transitioning to air source heat pumps will moderately reduce urban heat dome intensity overall, particularly in colder seasons, because they inject much less net waste heat into cities compared to fossil fuel systems. But different versions of the same machines, air conditioners, are actually responsible for heating up cities in the summer, with increasingly dangerous consequences. Thanks so much to Bob Krytov, Professor at the University of Warwick's Department for Engineering, for his help with the answer. Next time on Question of the Week, we're answering this from listener Christoph, voiced up by one of our team.
How does the UV filter in sun cream actually work?
And it goes without saying, if you have an answer to share with us or a question of your own, do send it in. It's chris@thenakedscientist.com. That's where we're going to have to park it for today, though. Remember to tune in on Tuesday when we're going to be delving into the science of hearing and hearing loss. Apparently, I learned this week, birds can't go deaf, at least not for long. We'll hear how they might be able to show us how we can repair our own auditory systems. The Naked Scientist is supported by Rolls-Royce and by all of you who continue to help us out so generously on a regular basis. Thank you very much indeed. Now, if you're not yet a supporter of this programme, we have just launched this year's fundraiser, and it is looking a little bit forlorn because no one's made a contribution yet. So please, someone, will you put it out of its misery? And also, write us a comment or two on the donor wall. If you can do that, we would be very grateful. You go to nakedscientist.com/donate. It's all safe and secure and happens on a dedicated third-party platform. That's nakedscientist.com/donate. I'm Chris Smith. Thank you to all of you for listening, and thanks to the Naked Scientist team for helping to put this programme together. Until next time, goodbye.